seats. So, not only the last joke, it will be given by a person. He comes from India. He's still a student, and he did the summer of code for Google. And at that time, he has the opportunity to dig into scientific computing and for JRuby, for instance. But also, he did a lot of work on GPU computing, and he developed binding for Ruby and JRuby on CUDA, which is a C++ framework for GPU computing. So you see that he has a quite good understanding of scientific computing. Please welcome him with me.
Thanks, Chris. Hi, I am Prasoon, and I'll be talking about scientific computing on JRuby. So the main objective of this talk is to tell you how to create a great gem or tool that uses JRuby and that's very highly efficient and has a very good speed. And this is all because a scientific library that I worked on is memory intensive and speed counts. So I'd like to share my experiences with that. Next, I will be introducing you to the general purpose GPU library that I worked on. And this was after my GSOC. And this library can be used for industry in production and academia for research. And yes, it can be integrated with Rails. So JRuby is also called as Ruby Science Foundation, and it has been trying to push Ruby for scientific computing. Some of the popular JRuby gems that we have currently are NMatrix, Daru, Mixed Models, Nyaplot, IPython Notebook, and many more. So these are the most commonly used ones. So what NMatrix is? NMatrix is a JRuby's numerical matrix core. It helps you to perform linear algebra calculations on your CPU, and it has support for both dense matrices and sparse matrices. Basically, it helps you to analyze matrices, which you might have studied in your high school, where you used to solve linear equations using matrices. And NMatrix for MRI relies on Atlas, CBLAS, CLAPACK, and standard LAPACK libraries for its linear algebra operations. These libraries are state-of-the-art libraries because they are written in Fortran and are highly efficient and are used for number crunching. So this is how you use an NMatrix gem. You just require it, and in the first one, second line of code, I create an NMatrix. This you can see that it's a two-dimensional matrix of 3 rows and 3 columns, followed by the elements it contains, and the type of the matrix is float 64, which is actually double. So double is used for scientific computing because it has a high precision, and you can't use simply float 32 or float. So I created a matrix of 3 by 3. You can see that it's a row measure format, 1, 2, 3, 4, 5, 6, 7, 8, 9. And in the next line of code, I just add these two matrices. And in the third line of code, I calculate the determinant of this matrix. Next, Daru. Daru is what Pandas is for SciPy. It helps you to load data into a data frame from say Excel file or CSV files or TSV files, and then you can analyze this data. So in this code, what I've done is that I simply require Daru. In the second line, I just load this data from alien_species.csv, and next I do is that I create a vector, and I just show this data frame. Now next is mixed models. So after you have loaded the data, maybe you want to perform some computations like model this data. So this can be done by mixed models gem, and in this code we try to calculate the fixed effects and random effects of this model, and thus we can also use this to predict for some random data. Next is Nyaplot. Any scientific library is not successful unless we have some great visualization tools. Nyaplot fills this gap for JRuby. It's used for 2D and 3D plotting, and it's built on the top of D3. Next, why you should use JRuby instead of SciPy? Simply because we love Ruby, we love Rails, and expressiveness of Ruby. You can use, when you collect a large amount of data from a Rails app, you can just feed this data into a Daru data frame, and then you can perform computations, and you can use this Daru as an analytics tool. Next is JRuby. My project was for GSOC was to port NMatrix to JRuby, and basically JRuby was trying to push its gem towards JRuby runtime because of the speed. It's actually 10 times faster than CRuby on certain aspects, and with Truffle Ruby it's around 40 times faster. And right now we just heard that it's gonna be around 26 times faster for just JRuby Classic. So this bird, I like to call it as the Roadrunner because I'm just dealing with speed, and I want to make this Roadrunner go beep beep. So NMatrix for JRuby. So NMatrix, for why I will build NMatrix for JRuby, because it has no global interpreter lock as in the case of MRI. So it's a very good team player. When you have a large processor with multi-cores, you can utilize them. The program you develop can be easily deployed with the help of Warbler gem. So you can use you can develop any gem on JRuby or any program in JRuby and just deploy it to your supercomputers or clusters what you have. And then JRuby has auto garbage collection. For whenever you develop a C extension for CRuby, you have to take care for garbage collection because you are dealing with large data. And when CRuby does the mark and sweep model, as we have heard in the previous talk, that this mark and sweep is not really good to handle. And when you have a very large matrix, say 2.5 million elements in a matrix, you can't really speed is at not good in such cases. Next is NMatrix for JRuby that I worked on. It relies on Apache Commons Math, which is a Java library, and it has very high good developer activity around this library. So MDArray. Before I built NMatrix for JRuby, we had MDArray that does this is an MDArray gem that was just like what NMatrix was for CRuby. It was the NMatrix for JRuby. So when we try to create a unified interface for NMatrix for Ruby as well as JRuby, just like Nokogiri does it, that you have a simple gem and you can run it on both instances. So we could have used MDArray and just built a wrapper around it for NMatrix. But indeed, this was not going to be a good idea because it used parallel called as a dependency, just like I use Apache Commons Math, and it was depreciated at the moment. And next is that every gem when you create with the NMatrix, you had to implement it using MDArray if I didn't build a wrapper around MDArray. So you have to put in more effort for optimization. For example, you have to check whether the data is not getting copied, like that. So how NMatrix works? Basically, NMatrix can be categorized into two parts: n-dimensional and two-dimensional. So this is how an NMatrix object looks like. You have its shape. That is, for example, I created a 3x3 matrix. Its shape is 3,3. Its D type is float, or it can be anything like int, complex, like that. S type is like whether you want to store it as a dense matrix or a sparse matrix. At S is basically the storage, the elements that go into a matrix. Now you have the add dim. This means that how many dimensions you have. For example, 3,3 is a two-dimensional matrix. Next is NMatrix architecture. Basically, we have a Ruby front end here. Then we have for MRI, we have a shared object extension.so, which is built using C and C++. Now this integrates with NMatrix C library, a native C library, which are CBLAS or CLAPACK. And this C library is are connected to the Fortran library, that's BLAS and LAPACK. So basically you have 3 layers, and this one, the Fortran library makes is what makes your computation go fast. For JRuby we have just extension.jar. It's built upon the top of Apache Commons Math. So for n-dimensional matrix, the major thing operator we had to build on it was element-wise operation. For example, add, subtract, sine, or gamma. In the first slide where we added 2 matrices, this was just going an element-wise operation. We iterate through the elements, we access the element, do the operation, and return it. So the major thing that counts here is you have your loops should be efficient. Means you can iterate throughout the array, and whichever is the first wins, whether CRuby or JRuby. So here in this slide I show you that when I created a matrix n1 and I just add them. So n1 plus n1 you get this matrix. For example, 1 plus 1 gets 2, 2 plus 2 4. Next, what were the challenges that were faced? First is autoboxing and and handling multiple data types. Second is minimizing the copying of data. So in JRuby we have this, that when we tried no strict typing, basically directly creating a data using JRuby code, we got this error. For example, in this case we have 2 arrays, we just add it, and if this array is smaller than 1, you start getting the values as 0. So I think Charles can answer me this question after this talk. And if I just simply add this any number greater than 1 to both of them, and I subtract -10, so I get the correct result here. So next is autoboxing. So what we did was as this project was in initial stage, I just dealt with the float 64, that is doubles only, because we had to deal with reflection, and that's all. Then for strict we created data types using Java, and we couldn't rely on reflection for large data. For example, if you create storage as array.new and storage as Java double with rows and columns.new, the second one will be definitely faster, because you know the size of the array, and you can loop faster through this the second array. So now we have autoboxing and enumerators. This is a classic case, because when we tried using NMatrix for JRuby for real data, for example, we have a 5 GBs of data which we get from a blog, and when we try to run it, we get an error here. You can see this highlighted code. I just created this array as array.new. So what happens is that you start losing precision. So if you just implement this in using Java code, so here you don't lose precision. Next is minimizing the copying of data. As we had heard in the previous talk from Charles, that JRuby takes more memory.
Can you go back one slide?
Yeah.
So what does that statement in yellow actually do?
So basically what we are trying to do is we take the storage. We are trying to build an enumerator that each with index. We have to get elements defined by indices. And if there are blocks passed, I just want to do some computation with it. So I just convert this storage to an array, and then I take the slice index and I try to push it in this array. And here we start losing values. For example, if we were trying to factorize a matrix. So every time you do it, if the value is 0.02 or 0.03, this gets to 0. And when you are trying to optimize something, and you have to iterate through this matrix, you have to perform the same computation through this matrix, it won't get optimized ever, because you can't just go to a convex point where this value converges. So you can't reach a minima. So next is minimizing the copying of data. So whenever you build a JRuby application, you make sure that you don't make copies of data, because already it consumes twice the memory than CRuby. So if you start making more copies and you have a larger matrix, it may totally destroy your GC. For example, there was a computation where JRuby takes around 50 seconds, and when I was just building NMatrix for JRuby, it took me around 1.5 hours. So, so after I made sure that I'm not making copies of data, I took down this time to 40 seconds, which was better than JRuby. So you just pass by reference, you just create a static method as helpers. For we will see this example later. So next is two-dimensional matrix. Now you have an n-dimensional matrix, and you want to perform certain computations, like you need to multiply two matrices, or you need to factorize it. Then we use we need to just cast this n-dimensional matrix into a two-dimensional matrix. So the basic operations here are dot, which is matrix multiplication, det for calculating determinant, and factorize LU means lower upper factorization. So in NMatrix MRI we have BLAST3 and LAPACK routines that are built in Fortran, but NMatrix JRuby was means it depends on Java functions from Apache Commons Maths. So the challenges were as follows: you convert an n-dimensional matrix into a two-dimensional matrix. So actually n-dimensional matrix is stored as a 1D array, because you can't just simply create a multi-dimensional array, because you can't just lay down them in the RAM properly. Now you have the array size matters, and you have to access the elements with speed, and you have to also take memory in consideration. So we have an n-matrix. I need to get a 2D matrix from this. So I use these helper functions. These are static methods from a matrix generator class called getMatrixDouble, and the array generator class has a getArrayDouble. So in this code, I'm trying to iterate over a matrix. Means basically a two-dimensional array. So I just benchmark this Ruby code. You can see that in the first line of code, sorry, we create a Java, basically a two-dimensional matrix of size 15,000 into 15,000. So basically, and I just benchmark this code where I initialize the value of this matrix as the index. So this takes me around 39 seconds, and then next I iterate over two arrays where I just copy the elements of one array into another. So this takes me around 65.12 seconds and 5.4 GB of RAM. So so when you have such large matrix, your RAM your RAM will be already consumed by that time, and you can't do it for any number crunching program. So yes. So and I do this similar thing in Java, and I get for this the time requires 0.031 seconds, and for when we have two arrays, it takes 0.033 seconds, and the RAM consumed is 300 MB. Hence, speed is improved 1,000 times, and memory is improved 10 times. And this is actually speed-wise better than JRuby, but memory-wise not as good as JRuby. It's JRuby has better takes less memory, but speed is slower. Next.
Also 15,000 is not a very large matrix, right?
Yeah, 15,000 into 15,000, which is 225 million elements.
Yeah.
So there's another gem, mixed models, that relied on NMatrix, and simply by porting NMatrix, I just ported this library to JRuby 2, and so you can model your data in JRuby now. Whoa. Now we benchmark NMatrix functionalities. These are the system specifications. I had an octa-core CPU and a 16 GB RAM. Next, in this graph, you can see that the number of elements in a matrix. This is, for example, 5,000 by 5,000 elements. We have 25 million elements in a matrix. And then on the y-axis, you can see the computation time. So lesser the computation time, the better the speed. So this is a logarithmic scale. So in this case, NMatrix JRuby is faster than NMatrix MRI. It is around 40 times faster. Next, for subtraction, we have the same case. It's 40 times faster. Next, for gamma, we have this, we compare 3, NMatrix MRI, then NMatrix JRuby, and NMatrix MRI LAPACK. You can see that on NMatrix JRuby, it's even faster than the Fortran code. And it's a lot faster, means it's 10 times faster than NMatrix MRI and MRI LAPACK, and for 400 times faster than this NMatrix MRIs. For NMatrix, for matrix multiplication, NMatrix JRuby loses to NMatrix CRuby or MRI, because we definitely don't have Fortran libraries for this, and so any Java code can never beat a Fortran code. Even though we have jitting, and this code will get improved after running a lot of loops, but still not get better than Fortran. Similarly, for determinants, it's again 20 times slower. For factorization, it's same 20 times slower. So these are the benchmark conclusions. NMatrix JRuby is definitely faster for n-dimensional matrices and 2-dimensional matrices when element-wise operations are concerned. But NMatrix MRI is faster for 2-dimensional matrices when you need to calculate the dot or determinant, or you need to factorize it. So how can we improve this? So the solution is that we also implement the backend of NMatrix JRuby with Fortran, and this time it will rely on Java native interfaces. And there was an option to use another library called JBlast, which is a JNI for BLAST libraries and LAPACK libraries. But when I tried to use them, it had a lot of bugs, and it was not it wasn't efficient enough. So this would be the final architecture of NMatrix JRuby. So we took this left side of this diagram to this right side, and overall, when we do this, when I tried to do a sample benchmark for this, it was actually faster than NMatrix MRI. So maybe in 2 months, NMatrix JRuby would be faster on all aspects than NMatrix MRI when I implement this part of the code. So also the future work includes implementing NMatrix for complex data type, and adding sparse support, and convert NMatrix JRuby enumerators to Java code for better speed. So overall, whenever you try to do any NMatrix, any computation using NMatrix JRuby, it would be currently as far as NMatrix CRuby, or even sometimes faster, because the overall calculations that rely on a single dimension, that would be faster in case of JRuby, and obviously JIT. So am I done? Nope. Enter GPU. So after Google Summer of Code, I wanted to go even faster for number crunching, and that's why I thought of implementing a GPU library, a general purpose library for GPU computations. And the aim of this project was to combine the beauty of Ruby with transparent GPU processing. And yes, this will be tested on both client computers and on servers that make use of Tesla's and Intel Xeon Phi solutions. Before this, there was no Ruby project that that was good for GPU computation. Maximum you could do was add 2 matrices using GPU, and that also was for 1000 by 1000 matrix. But yes, the ArrayFire library, that RB library that I developed, can handle around 15,000 into 15,000 elements matrix easily, and we are yet to test it on supercomputers. So what is ArrayFire actually? So ArrayFire is an open source GPU library that is written in C++ and uses JIT. So using JIT makes it even faster than CUDA and OpenCL. So yes, the competitors PyCUDA and PyOpenCL would be slower than ArrayFire RB. ArrayFire has also bindings to Python, but ArrayFire Python is built using Python. So whenever you try to do this, this code is really not tested, and try to do some computations using ArrayFire Python on my system, and actually most of the times the program hanged. So yeah, and when I did the same thing with ArrayFire Ruby, when I built it for MRI, it was working properly, and the speed was awesome. So next is ArrayFire Ruby can also help you to just go computing without writing kernels. So whenever you try to do GPU computing, most of the time you end up writing kernels, and this is where most people just leave GPU computing. But in ArrayFire, you just have ready-made formulas, and it can handle matrices of any size. It automatically scales. So how do you use ArrayFire Ruby? So you just in the first line of code, I just created an ArrayFire matrix. It's a 2-dimensional and 2 rows and 2 columns. I just add these two, and in the next I show you how we implemented blast routine, where I multiply 2 matrices, and then in the third part of the code shows how to get the determinant of a matrix. So let's see how its ArrayFire Ruby is built for MRI. It's a C extension, and the architecture is inspired by NMatrix and NArray. Basically, ArrayFire is written in C++. So when we try to build this library, we need to handle C++ code. So for that, these instructions help you how you can do it. And the important point to note here is that you just get rid of this mangling errors in C++. For example, this is how I implemented matrix multiplication. I just included ruby.h, and I created a data structure for ArrayFire, ArrayFire object. Then I just bind it to Ruby frontend in init ArrayFire. I create a function called ArrayFire. So this is being casted here because this is being this code is actually in a CPP file, and what Ruby frontend expects it is to be in a C file. So next I do an ArrayFire. So this finally goes to this line of code where I just multiply it. Here we can see that this line is for whenever a GPU computation is done, it's done on a GPU RAM. So you need to get this memory into the CPU RAM. So this line helps you do this. So when we try to integrate ArrayFire with Rails, this line would be very helpful. And you may be wondering that why GPU computing on Rails? Because you have data, means you collect data through active records, and now you can just analyze it. For JRuby, the approach is same as NMatrix JRuby. We have a Java native interface for ArrayFire already built, and even I implemented some of the BLAST and LAPACK routines. This works on ArrayFire Java. What you have for example, the last example we saw where we did matrix multiplication using C code. This can be easily implemented in JRuby just using this part of code. So here you can see that how awesome JRuby is. Now we benchmark ArrayFire. System specifications are as follows. We have same octa-core processor with 60 GB of RAM, and GPU was NVIDIA GTX 750 Ti, and RAM is 4 GB DDR5. So in this I think you can see it here, and this is around 10⁵ times faster than NMatrix Ruby, and 10⁴ times faster than NMatrix JRuby. And again, ArrayFire is faster even here. It's around 10⁶ times faster. For matrix determinant, it's around 100 times faster. Even for factorization, ArrayFire is 100 times faster. So transparency. Actually, the current when you try to find ArrayFire on GitHub, you can see the code written only for MRI. For JRuby, I have already done the groundwork. It just needs to be in the repo now.
Can you go back to those figures? Because I think you were a bit too fast.
Okay.
It's more than 100 times faster to me.
Okay, maybe 1,000 times faster.
Yeah.
So transparency, we need to integrate it with NArray and NMatrix and with Rails. So where I showed you that you just copy the RAM from GPU to CPU. You can just create some function methods for that, and yes, Rails is now on GPU and similarly as NArray and NMatrix. So what are the applications? Actually, ArrayFire has endless applications. You can use it for bioinformatics. You can integrate it with TensorFlow when it's ready. So you can just create a GPU cluster using ArrayFire and integrate it with TensorFlow. You can use it for image processing. You can use it for computational fluid dynamics. So hence, beep beep. These are the useful links. You can go to for NMatrix. You can find it here, and ArrayFire RB is here. And the latest code can be found on ArrayFire temp branch. I would like to acknowledge my mentor Jotter Prince and Charles Nutter and John Woods who have been very helpful to me in creating these libraries, both ArrayFire and NMatrix. Next is Alexei Gossman, who developed the mixed model gem. Sameer, he's the developer. He developed Daru. And then we have Pradeep Garigipati from the ArrayFire team. He's also mentoring me with this project. So also I would like to thank Emerging Technology Trust, that is the organizer of RubyConf India, and currently they have sponsored my travel to FOSDEM. And thank you.
Thank you very much, Professor.
Okay.
We have time for questions. Please.
Yeah.
Did you consider other libraries like Boost, SIMD, or VC for the parallelism using the hardware?
Hardware for what? NMatrix or ArrayFire?
For the sending more than one value to the processor for the computation should be done faster.
Your question is basically that I need to send the values to more than one cores for processing, right?
Yes.
So basically, this for NMatrix, it is done by Fortran, and Fortran is already optimized for this. It lays down memory in certain way that it uses parallelism for that. So yes, it's done by that way, and a Java code can beat that code. Okay, next.
Actually, Fortran doesn't use MMX or other processor instructions created by that after the Fortran language was defined. The Fortran libraries are really old for that. Usually you have now two libraries in C++ that are able to do that because they know how the processor was built. The name of those libraries are VC and Boost SIMD.
Okay.
If you want to take a look on them later.
Okay.
And there is also one library that I helped to write for matrix processing named Eigen3. That's really fast, and I think
it's for R. Eigen3 is for R, right?
Sorry, I didn't understand.
Eigen3 is for R.
Yeah.
R language, right?
No, Eigen3 is C++.
Okay, but R uses it mostly.
Yeah.
RCPP and R Eigen. So yeah, I think that's slower than LAPACK and BLAS. Okay. Next question. Yeah, yes.
Great work on this stuff. Just a request.
Okay.
Anything that looks like it's a bug or you've got problems comparing to MRI, even if you're not sure, just go ahead and file a bug.
Okay.
We'll be able to tell you right away if there's any problem. Like that matrix thing is weird.
Yeah.
I don't know, we are poking around in the
Okay, so basically the problem is that even I don't understand whether the problem is with JRuby or it's JVM. So
right. It's probably us.
Okay.
We always just assume it's us. So.
Okay.
But you added two arrays, and normally that plus would just concatenate those. So do you override?
No, I didn't concatenate those. I just add these two elements. Means 2, 2. For example, the array has 2, 2, another has 2, 3. So we get the final array as 4, 5.
Yeah. Yep.
Means 1. Okay.
And it's just not adding. It looks like it's coercing into fixed numbers.
Yeah. Yeah. And actually, this can't be reproduced. Sometimes you get 4 out of 10 times you get a 0, or else it works fine. Yeah.
What do you see as the integration of this with Rails?
Yeah.
Well, like what kind of integration do you think you can do? I didn't understand.
So basically, if you have some, maybe you can try it with active record. Basically, I've not consulted I consulted some Rails developers at RubyConf India, and they had inputs like we can do it with Rails, and so it would be widely used.
Other questions? Thank you, Preston. A very good presentation. So our last term.